Alright, so today we're going to be doing 5.2b, which is definite integrals using shapes. All of this is a recap of what I talked about in more depth yesterday. This is just understanding that Riemann sum is basically addition of some amount of rectangles under the shape. When you integrate, you are basically adding those infinite amount of rectangles. If you have infinitely many rectangles, you can actually get the exact area underneath the curve. And this right here is just the limit definition. This is what we talked about yesterday. This is how you understand the notation of an integral. And then this we didn't talk about yesterday, so I'll talk about it briefly for you to help understand the connection between derivative and integral. So we know that derivative finds the rate of change of a particular function, and we can find the instantaneous rate of change by plugging in any x value into the derivative, which tells us that exact rate of change. And does anyone remember what we call this right here?
Tangent line.
Tangent line, good. Now, with an integral, we're essentially finding the area underneath the curve, between the curve and the x-axis on any given interval. So from, in this case, b to c, we're finding that area underneath the curve. Now, yesterday we learned that we can do this analytically by taking the antiderivative and plugging in the endpoints and subtracting them. But today we're going to talk about why and when we can use geometry to actually find this area. So, the reason that we do this is because sometimes, well, actually we're not there yet, so I'll get to that part in a second. So let's talk about net area and how this works. So in geometry, in all the math classes you've gotten to up to this point, you know area has to be positive, right? But remember, when we find the area under a curve, we're not truly finding area. We're using area as a tool to find the space under the curve which represents something else. Okay, so it can be negative, and I'll talk about when that is. So any area that exists above the x-axis is considered positive. Anything below the x-axis is considered negative. So this is what it looks like when a total net area is positive. The portion of the shading above the x-axis is greater than underneath. Total net area is going to be negative when the larger portion is below the x-axis. And its net is 0 when they are the same size above and below, which will end up being 0 and balancing each other out. Does everybody see why that is? Okay. So, common geometric formulas. The ones that I'm going to have you use the most in this class is rectangle, triangle, and circle, and manipulations of those formulas. Those are ones that I would expect you to know offhand without me providing them for you. Trapezoid, we use a lot too, but keep in mind a trapezoid is just a rectangle with triangles added to it, so you don't actually ever have to technically remember the trapezoid formula. You can always do it with a rectangle and a triangle.
2 triangles.
Sometimes 2, sometimes 1, yes. So that one you can always work your way around. We don't do too many ellipses in here. Equilateral, if I ask you to do it, I'll give you the formula. All right, these are 2 important graphs. These are common on AP. I know you guys aren't in AP, but the idea here is a semicircle. The radius is always whatever this number is. I'll talk about how you don't have to memorize that. You can just see it from the graph. And then we have the absolute value graph, which is going to look like this. So it's going to be 2 rectangles. All right. So first one we're going to look at here. Now, depending on how familiar you are with function families, you may know this is a semicircle, half circle. If you're not, that's okay, because we can always plug in points to see what this graph looks like. So you always want to plug in the endpoint. So if I plug in 2, what's 2 squared? Yeah, it's going to be 4 minus, each of 4 minus 4 is 0, square root of 0 is 0. So this is at 2, 0. Now, is that going to be any different if we plug in negative 2?
No.
No, because you're squaring it. What about if I plug in 0? What am I going to get?
2.
2. Now, you may automatically think this is going to have that triangular shape to it, but it actually doesn't, because if you were to say plug in 1 or negative 1, you're going to get the square root of 3, right? If you put the square root of 3 into the calculator, that's 1.7. That's about here. This is actually a semicircle. And you can start recognizing what a semicircle formula looks like. That semicircle always will have this kind of appearance to it, square root of something that's squared minus something that's squared, okay, variable. So our task is to find the area between the x-axis and the function. Now, we learned yesterday that we can take the antiderivative and plug in the n values and subtract them to get the area under the curve, correct? But do any of you in here know how to take the antiderivative of this? No, this is complex. This is something that is more you learn towards the end of calc, sometimes calc 2, to take the antiderivative of. There is a way to do it. It's called U substitution or integration by parts. We probably won't get to it in this course, but be aware there is a way to do it. But what we're going to do is we're going to use other tools to help us find exact areas that don't require that. So, why would we do all that difficult integration when I can simply use a geometry formula to find out what this area is, right? So this is area of a circle, which is pi r squared. But there's one variation to that. What's the difference between this shape and this being a circle? It's only half of it, right? So it's going to be pi r squared over 2. What would be the radius of this circle? 2. Everybody see why this right here is the radius? Now you could have also found the radius because it's always the square root of this number right here in the formula. So either way that you want to find that is fine with me. So that's going to be 2 squared over 2, which is going to be
2 pi.
2 pi. So does anybody have any questions about this?
Nope.
Okay. All right, next one. Can you guys, like, with the crinkling? Thank you. I feel like I'm at the movie theater.
What?
The crinkling.
Crinkling.
Yes, the crinkling, digging for the perfect Chex Mix piece over there. All right, so this one here is an absolute value function. You may or may not know what this one looks like, but a few things. You can always plug in the endpoints if needed to get what, those endpoints are, right? So let's say we plug in -3. What's the absolute value of -3?
3.
3. What's 1 minus 3?
-2.
-2. So we know at -3 we're at -2. What's the absolute value? We're going to plug in the next one. What's the absolute value of -2?
2.
1 minus 2? -1. What's the absolute value of -1? 1 minus 1 is 0. What's the absolute value of 0?
0.
1 minus 0?
0.
1.
1.
Then here it's going to be 0, right? Yep. Then 1 minus 2, which is -2. So I'm only going to graph it from here to here. Why did I stop on this particular section?
That's the way for the function.
Yes. Like that. All right. So once you have the shape of the graph, remember, you're only going to find the area of the space between the graph and the x-axis, which is here, right? It's going to be here. And here. So does everybody see how I was able to find those 3 spaces? So we're going to find the area of each of these spaces individually. What kind of shape is this? Triangle, so it's going to be 1/2 base times height. The height is 1. The base is 2. So that gives me 1. Everybody see how I got that? This one here is going to be also a triangle. Crazy. So 1/2 times 2 times 2, right? Height,
I think that's 2.
it is 2.
I'm so good at that.
But it's not just 2, it's actually what?
-2.
-2, because it's below. What's the area of this one right here? Not -1. -1/2. So does everybody see how we found those 3 areas? I'm just doing base times height, base times height, base times height. With a right triangle, base times height are the 2 legs. With any other type of triangle, the height is going to be the actual height of the triangle. You guys all know that.
You're including the negatives?
Correct.
Everything?
The negatives are always anything that's below the x-axis is going to become a negative area.
It's like when you plug it in as a negative? Just turning the answer into a negative.
Whatever you feel better about. I just make the end result negative because I think it's easier if I know that it's found below the x-axis. Okay, so now that I have the total areas, I'm just going to combine them. So 1 minus 1/2 minus 2. That gives me -3/2, right?
Yeah. Why not?
So what that means is if you knew how to take the antiderivative of this function and you were to evaluate it from 2 to -3, you would get -3/2 as your answer. Because what we did, we found the exact area. This was not an estimation. Do you see how this is not an estimation like the ones we had done previously was? Okay. So next one we're looking at is an absolute value over an absolute value. So with this one, we can do the same thing. We can plug in some values, okay? So let's say we plug in 3. We've got the absolute value of 3 minus 1 over 3 minus 1, which is 2 over 2, which is 1. So I have a coordinate 3, 1. I can plug in some values in the middle here. Let's say I plug in 2. I got 2 minus 1, which is 1. Absolute value of 1 is 1. 1 over 1. It's 1. Any of these I plug in on this side. But here's the problem. What happens when I plug in 1?
0, 0.
Can we do that in math?
No.
So this is an open circle because it technically can't be graphed. But the reason it's an open circle is because it's a continuation, okay? Now here's the trickiest part. If I plug in 0, I end up with -1, absolute value of -1, which is 1. 1 over -1, right? Which is -1. All the next ones I plug in from here are also going to be -1 because I'm plugging in a negative number. And -2 would also give me a -1. Now, we have a general idea of what this is going to look like, but do you see how we have this gapping here in the middle? We're not sure where this would go. So what you have to figure out is, are these values in the middle between? Are they going to be above or below? Which one?
Wouldn't it be 1, 0? Or do I not know how to subtract?
Why can't we plug in 1? Is that what you're wondering?
No.
-1 minus
1 minus 1, 0 over 1
Yeah.
minus 1, 0. Why do you
Yeah.
put it at 1?
Because it's indeterminate form. We can't, 0 over 0 isn't 0. It's nothing.
Okay.
Oh, you're wondering like why did I know where to
Yeah, what's
place
up there?
it?
Yeah.
I see what you're saying. So that's actually what I'm talking about now. We have to kind of figure out where it's going to be placed. So what we have to do is we have to find a value in the middle of these two right here so we know where to go. So, yeah, it's kind of weird. No, it's okay. You're good. So what if we plug in a 0.5? Okay, what if we plug in a 0.5? 0.5, is that going to give me a 1 or a -1?
1.
A 1. No.
Yeah. That would be positive or negative.
Positive over negative. It's going to be a negative. So every point up to the 1 is going to be a negative because if a number is smaller than 1, when you subtract 1 away from it, it's going to be what? Negative. So that's why it doesn't actually really matter if you want to place the open circle here or here. You could place it in either spot because what this is going to look like, it's going to look like this regardless. Does that make sense? I know this one's kind of tricky to think about. This open circle, you can choose to put it here or here because it's going to give you the same graph. I know, that one's kind of hard to wrap your head around. But does everybody see how I was able to come up with the graph? Because you could even leave this, not even put a point for 1. You get really, really close to it, it's still going to be on the bottom until you get to 1. When you get past 1, it's going to jump up. So we call a step function. So does everybody see how I came up with that area shape?
Okay.
What's the area up here going to be?
1.
1 times
0.
2. What kind of shape is this?
A vine.
A rectangle. We're finding the area of the shaded region, right? So 2 times 1. So you always shade the region between the function and the x-axis.
99999.
This doesn't Oh, you're saying because of this portion?
Yeah.
Right here?
Yeah.
Well, here's what's going to happen is the area is fully completed.
Or
Bec-
1.999.
I see why you say that, but it doesn't matter because on the bottom it's also going to be equally as close to this side. So because of that, they're going to match up. If that makes sense. Maybe not. It's weird to think about, yeah. This is 1 and this is 3, right? But this one's area is going to be what? Negative 3. So what's my total area here? Negative 1. Yes.
Why wouldn't it make a difference if the open circle's on the bottom?
Because we don't, if you guys want to throw out the open circle, we can literally take it out. It doesn't matter.
Isn't it 2 plus 3?
Area.
No, she did 2 minus 3.
That didn't answer my question.
It doesn't matter where your open circle is. You don't have to graph the 2 at all, or the 1 at all. If I plotted 1.9999999, it's going to be negative 1, right?
Mm-hmm.
If I plotted 1.00001, it's going to be up here, right? So we don't really care about what this one's at because it's jumping from the next section. Yes.
Where did the 2 minus 3 come from?
Yeah. I have a
You just
question
added
too.
2 areas up.
Yeah, you just,
Subtract them.
it's adding a negative, so it's the same thing as this.
Oh, okay.
So if you want to think of it more as addition, that's fine too. It's going to give you the same result.
We subtracted in B.
What?
We subtracted in B.
It's just me adding negatives. What's up, Paul?
Maybe special.
Yeah. Yeah, so like I just kind of skipped that step, but I see what you're saying. Yeah, you're technically adding them together. It's just when you add a negative, it just becomes subtraction.
Yeah, I got it.
Okay. Is everybody good with that? Don't overthink this one too much. It's not going to matter because even if this one's marginally smaller over here, because it's cut off, and marginally smaller, they're equally amounts of marginally smaller on each side, correct? What's happening?
The pass got stuck on the door handle.
Oh, I was like, is somebody in a fight out there? All right, anyways. This is very chaotic. Okay. So,
Just keep checking.
does anybody know what kind of function family this is? Starts with an R. We have a whole unit on it in Algebra 2.
Right triangle.
Not radical, but it sounds similar to that.
Radian.
R-A-T. Rational functions.
A rat fight.
Yes. A rational function is any function where you have a polynomial over a polynomial. Okay. So why did I write it like this? What am I going to do with the top?
Factor.
I'm going to factor it. Why would factoring this be beneficial?
You cancel it out.
Cancel it.
I can cancel it out, but not without consequence, okay? When I cancel something out, what does that create in the graph?
hole.
A hole. You remember discontinuity? There's 2 types, removable and non-removable. Don't know how much hopefully it's coming back to you a little bit.
Coming back.
So we know that x cannot be negative 2. To find out where the hole is, we can simply plug it back into our function, the new function, of course, to see where the hole is going to be. So where's the new hole going to be?
X minus 2.
Correct, but what's the y value of the hole? You can plug it in here. Negative 4. So at negative 2, negative 4, we have a hole in our graph. Now, holes don't affect the area because the area is still going to be the same because, remember, it's only a hole at that little tiny point. Everywhere else is still filled in. Because I know you see the hole, it looks big, but it's really only at a tiny little point. So now you can graph this function. Now, what kind of function is this? Linear with a slope of 1 and a y-intercept of?
-2.
Good. So I know I can start at -2, down or up 1 over 1 at 1, and then I can continue it out by going the other direction, right? And I go from 1 to -3. So everybody see how I graph that? Just graphing a linear function. But only from -3 to 1, because that's the only place I want to find the area to.
Makes a triangle.
Not a triangle.
What? How do you not make a triangle out of this?
Yeah, that's a trend.
I can make a triangle.
I promise it's not.
Oh, you
Would it
see
be
how
trapezoid?
it's exactly, yeah.
Oh,
Oh my
okay.
god, guys.
I thought it was a trend.
I could have.
You guys are like, yes, it is. I was like, okay. So you have two options here. You can either choose to use the trapezoid formula, but for me personally, I like to not have to remember extra things. So what I do, and you can choose what to do because it's your life, I like to split this into two pieces. I see that I have a rectangle up here, and then down here I have a
Like I said, triangle.
Oh my gosh. Part of it's a triangle.
part of it is, but the whole thing is below the
Y-axis.
the x-axis.
That's
It
crazy.
can't be below the y. It's okay. So the whole thing's gonna be what?
Negative.
Negative. So what's the width of this rectangle?
4.
What's
One.
the height of it?
1.
1. And then the triangle is gonna be 4 and 4. So this area is 1/2 times 4 times 4.
8. -8, really.
Yep. And this area is just
Negative
-4 and -8, right?
It turns into 12. -12.
-12. The whole thing is -12. Make sense? Hopefully? Any questions about it? Okay. Don't get too hung up on the step function.